Good morning, everybody. Welcome to our first press conference of the day. This one is about Rosetta Comet science results, and our speakers in this order will be Matt Taylor, Rosetta Project Scientist with the European Space Research and Technology Center in Noordwijk, the Netherlands, Claudia Alexander, U.S. Rosetta Project Scientist with NASA's Jet Propulsion Laboratory in Pasadena, Catherine Altweg, ROSINA Principal Investigator at the Center of Space and Habitability at University of Bern in Switzerland, and Jean-Pierre Bibring, Lead Lander Scientist at the Institut d'Astrophysique Spatiale at Orsay, France.
Okay, thank you, Peter. I'll kick off with a brief overview of where Rosetta is and what it is. Certainly, I was here at AGU last year before everything happened. We've had a long journey to get where we are today. This is a graphic indicating the 10-year journey, over 10 years, that Rosetta's undergone to get to its target comet, Churyumov-Gerasimenko. The 10 years were nearly up this year, or as we began this year, and in January we came out of hibernation and began a number of getting to a number of milestones operationally. Those were the coming out of hibernation in the first place, the rendezvous with the comet in August, and then mapping the comet and landing on the comet. At the beginning of the year, on the left, is what we thought the comet looked like, and very quickly we began to become familiar with this other shape on the right-hand side, and we have some examples of these as well on the desk here. In that time frame, we also had to select somewhere to land on the comet in a significantly compressed time frame. Again, if you can consider that in January we didn't know what the comet looked like, so we had an accelerated process of mapping the comet and also making a decision where to land. These are the orbits around the time of the landing. Basically, we were doing very close orbits, around 10 kilometers in the terminator plane. Then we kicked out to do a pre-delivery orbit to go out to about 30 kilometers, and then deployed the lander at about 23 kilometers, and most of you know what happened then. Just give the most recent NavCam image that we have. This is actually from 5 a.m. yesterday CET, so I guess it's 9 o'clock Tuesday, local time here. This is showing the northern lobe, the head of the black swan, or the duck as it were. Also you can see or pick out where Site J, where the original landing was, and then over on the far right is also where we believe the lander is at the moment. And this is just a montage of the separate frames. So I will pass over to Claudia now.
Okay. So what I'd like to do is set the stage for what we're going to hear from our principal investigators of the instruments by talking a little bit. Let's go to the next slide. So I'm going to remind people that we have pretty much two populations of comets, or two comet homes. And in the purple, we have the Kuiper belt. We think our comet is a Kuiper belt object. And in the golden yellow stuff, we have, this is as the Natal forming cloud has collapsed into a disk, and the protoplanets are forming around a proto-sun, and there was a lot of debris in the inner solar system and in the outer solar system. And we think that in this particular model, which is called the Nice model, just one example model of how the solar system formed. But we think in this model that the orbits of the outer planets were unstable, and the two most outer planets, Uranus and Neptune, changed places at some point. And in that event, where the orbits switched, it was a cataclysmic orbital disruption that cleared out all the debris in between Uranus and Neptune and Jupiter. So we'll see that here in a minute. But that left the Kuiper belt largely unchanged. And we think that so we have what we think sampling the outer solar system, the Kuiper belt, and we have other comet populations that sample an innermost or closer to the sun population and chemistry. Next slide, please. In that cataclysmic event, we think that possibly there was a rain of comets that hydrated the Earth, the forming Earth, And so some of the measurements that Rosetta was sent to obtain were going to help us understand if that was true, if that was part of the solar system history as we understand it. So hopefully Catherine will address that later in a few minutes. Next slide, please. I want to remind you that comets are dusty objects. As they go towards the sun, they fill up the space around them with ice and dust ejected from the surface in various physical processes, including sublimation, and that we really want to examine the grains that are coming off. And the next slide shows us some of these grains. We think that cometary material is perhaps a refractory, sort of silicate material that has an icy veneer of various ices, also with organic material in it, that after bombardment with cosmic rays and ultraviolet light over the course of geologic solar system time, that you form a cometary grain that has this various envelopes of organic material, icy material, and refractory material of some kind. And it's those grains that we want to examine for this kind of content, which is going to be a sampling of the outer solar system. Next slide, I want to mention that part of what makes this kind of material that the comet is made out of mechanically strong, when you have these kinds of icy grains, is a process called sintering, in which the grains have contact with one another only in certain places. And it turns out that that kind of material can actually be quite strong. And I'm hoping that Jean-Pierre may talk about this a little bit later in this presentation. And that's all I have to say today.
Good morning. I'm the principal investigator of the ROSINA instrument. Actually, next slide. ROSINA is 3 instruments, 2 mass spectrometers, and a pressure sensor, density sensor. It's a very international instrument. It's led by the University of Bern, Switzerland, but it has co-investigators and hardware from all over the world. I'm talking today mostly about the COPS, the pressure sensor results, and also the results from the DFMS, from the very precise mass spectrometer, which can look at details in the composition of the comet. ROSINA is on the orbiter, it's not on the lander, so we are still measuring, and we started to measure already in August. Next. So that was the first signal we saw from the comet. That's the comet pressure sensor measuring the density. You can imagine you have a comet, you are a certain distance from the comet. We started out to see signals at 200 kilometers from the comet, and what we saw was a modulation of the density, which really surprised us to start with. We didn't expect it. But soon we became aware that the modulation has a period, actually 2 periods. It has 12.4 hours, and then a smaller peak at 6.2 hours, and we recognize that this is the rotation period of the comet. So what we see is we see the comet rotating in front of the instrument, and sometimes we see just the head of the duck, then we see the large side of the duck, then we see the bottom of the duck and the other large side. So the area which is facing the spacecraft and which is illuminated by the sun is changing with the rotation period of the comet, and that gives a density variation in the coma. That's nice to see, and it tells us. What you also see is that sometimes the modulations are high, sometimes it's lower. That's summer and winter hemisphere, or hemiduck. It's not a sphere. So if we are in winter, the modulations, the signal is much lower and the modulations are lower. If we are in summer, then the modulations are much higher. Next. What was also very surprising was the rich chemistry in the coma. We blocked this, the comet stinks. Yes, it does, but that's the popular vision. Of course, the scientific vision here is that we did not expect heavy molecules already that early in the coma. 3.5 astronomical units from the Sun, we expected to have mostly the supervolatiles, which is CO, carbon monoxide, and carbon dioxide. But as you see, we have all kind of molecules, up to relatively heavy ones. If you have CS2, carbon disulfide, it has a mass of 76, so that's rather heavy. That's, of course, not all. We have a rich spectrum. From ROSINA, we have signal on all integer masses, but it takes a long time to really analyze because many of them are just fragments from even heavier molecules. So that's what we are sure about today. We have a few more which we are sure, but for most of them we still have to analyze to see what we get in the end. Next. One of the first measurements we made was actually the deuterium in water. Of course, that was one of the big goals of ROSINA, and ROSINA is a mass spectrometer which really can do it without any assumption. So far, all measurements of the overaging comets had to assume the oxygen isotopic ratios, and ROSINA is the first one who does not have to assume. That's the picture we have in the solar system, or at least what we believe we have. We have asteroids inside of Jupiter, actually. Then we have Oort cloud comets. They originate inside of Neptune, but are now very far out. But the original formation was done probably inside of Neptune. And then we have the Kuiper belt comets, where the formation took place outside of Neptune. We have DOVH. The first time it was measured was almost 30 years ago with the Giotto mission at Comet Halley, and it was recognized that the DOVH in Oort cloud comets is twice the terrestrial value. And at that time, I think the theory that the Earth got its water from comets somehow disappeared, especially because in the following years, in the 90s, the big comets Hale-Bopp, Hyakutake, and a few other Oort cloud comets showed a similar high deuterium to hydrogen ratio. And this theory only reappeared about 3 years ago, when the first Kuiper belt comet could be measured. It was Hartley 2 from the Herschel spacecraft. Hartley 2 is a small comet, but a very active one, and it came very close to the Sun. So it was possible to measure it from remote. And surprisingly, it had a terrestrial value, exactly terrestrial for the deuterium to hydrogen. So now, of course, it was quite interesting to see what our comet would say to the deuterium ratio. Next. So that's not the right one.
That's all I've got in here. Was it? Yeah, you not good. I haven't got.
Oh, okay.
Shall I go back to that?
No, that's okay. So when we measured it, we saw that we could, over the whole 10 years of the cruise phase, we measured water. We measured the water of Rosetta. Rosetta was outgassing. And our instruments are sensitive enough to see the outgassing, and probably not surprisingly, the DOVH was terrestrial. So Rosetta is really a terrestrial object. But as soon as we got to the comet, we saw that the water is different. That the DOVH is much, much larger than in Oort cloud comets. It's more than 3 times what we had on Earth, what we had before on Rosetta, before we were at the comet. So with this, I think we can come to a conclusion that not all terrestrial water can come from Kuiper belt comets. It does not exclude that some of the terrestrial water comes from Kuiper belt comet, but most of the water has to come from somewhere else. And as there are models which show that asteroids could have delivered the water. I think that's the way to go, and probably also the way to look for water as the origin of our terrestrial water. So that's not all. We are going on. Next. The mission continues for ROSINA. It continues at least until the end of 2015. The Comet at the current time is still somehow sleeping. So the outgassing is weak, and it did not really pick up since August. But now we are going inside the so-called snow line. It will certainly become much more active. We expect a factor of 100 from now to next August in increase in the activity. And of course, that will give ROSINA a lot to measure. What we want to deduce is something about the structure of the comet. You can do that by studying which molecules come out when, where. The layering of the material in the comet nucleus, and of course also the heterogeneity of the nucleus. You know that some people claim that these are actually two comets. And if so, they might have some heterogeneity, some more of the one material here than here. And finally, I think we picked really a very good comet. The material we are seeing is extremely pristine. Everything points to very, very cold temperatures. So next. We are looking at other isotopes, so not only the overage in water, but the overage in other molecules, and also other isotopes like oxygen and nitrogen. We are certainly looking for organics. We have already found quite a few of them. We are looking for noble gases. Also here, we are finding them. We are analyzing it, so I can't give you a firm value today, but that's soon to come. And the comet really surprises us almost every day with new results. So we are very happy about this comet. Also, it was not the comet we wanted to go in the first place. But I think it was good that we missed the first one. Jean-Pierre.
My turn?
Yep.
Mesdames, Messieurs, thanks a lot to be here. It's really, as I always say, but I think more and more it's true that I'm very moved to be here and honored to be here with you. I met already some of you overseas, but not all of you. So I'd like to state first that there is really a message to get home. And we are so rapidly used to what happened that really we forget what happened. And a few months ago, we had a dream, and this dream really became reality. And this dream was really to land somewhere in a very pristine body to try to decipher the processes, what are the ingredients that pave the way to the diversity of the solar system as we see it today, and actually beyond the solar system, the solar system themselves. We'd like to know why there is such a diversity, and in particular, what are the building blocks of life, and possibly the comets might answer that. So that's what the reason why at the first place we want to get there. And as you know, we made it finally. It was not a trivial endeavor, as you probably all know. It was not obvious that we would be able to do so, in particular because although we say that ESA landed, it's not really ESA per se. It's ESA plus the Philae consortium that was built to make an instrument. It was built as an instrument in the first place. And so we didn't really have all the possibility to build something with all the flexibility we'd have loved to have there. So for the first time, we put together something which is man-built, 20 years old. It looks old. Actually, yes, we started that 20 years ago. We were much younger. And we finally went on the earliest body in the solar system, we think. It's probably, has just been emphasized, something which we never saw before. We never had the possibility really to know what the pristine material out of which the entire solar system was built there. So this is what we wanted to. That's where we are. So where are we now? We all know that Philae has entered a rest. It's normal after all what has happened in November. It has to recover a little bit. And we had the capability to operate all the systems and instruments. I will go back to that, of course, in a while. And meanwhile, which is only a few weeks ago, we have started to analyze all the data, both the scientists, the engineers, the technicians, everywhere, because there is a lot of data together. And of course, one of the key thing here is the very collective things. We really merge as much as possible science and technology to understand where we are. And at the same time, we are preparing for the post-hibernation, because whether you like it or not, we will wake up and hopefully in a very good shape. So what is the science that we'll really had up to now? We had 3 levels of science, one during the descent itself, what we call the SDLs, separation, descent, and landing. Then we have something that we did not expect, the science just by the bouncing, the rebounding, give a lot of science there. And then the science that we made in situ afterwards. And if I start with the SDL science, essentially all went exactly as planned. So we have all the instruments that we wanted to be operating have been operating from top to down. And I'm just put the emphasis on 2 of them here, the ROMAP and the ROLIS instrument. The ROMAP essentially has different possibility, but in particular to measure the magnetic field from the orbit down to the comet, and that's been done perfectly. Very often now you see people speak of ROMAP as a tool to, in particular, and I will go back to that, it helped us understanding the rebounding and everything. That's true. But more than that, it's really a very good scientific instrument. The sensitivity of ROMAP is such that they can measure with a huge accuracy the interplanetary magnetic field, the solar wind, in all 3 directions. And this is why we recovered the position after the bouncing, because we could really follow the rotation and measure the rotation velocity. But more than that, we have the very good understanding of the variation of the magnetic field from orbit to there. And of course, the goal there was to know whether or not there was some magnetization in the comet, because as you might know, it's a key parameter to understand how the solar nebula actually collapsed, whether or not it was a magnetized body or not. And we are very close to have the answer. And that's of course is what I say here. Of course, it will come very soon. You can understand that the peer review process that we are so forced to go through, which is very important, is not completed yet, but very rapidly, I think it will be one of the major outcomes in the coming days or weeks that you will get from the ROMAP. So ROMAP was very powerful. We have the ROLIS descent imaging here, which is an instrument that will also designed to make the imaging of the surface while we descended from a few kilometers down to a few meters, and that worked superbly. And so the same sight we have from almost meters resolution up to sub-millimeter almost, or millimeter resolution when we touch down. So we had the possibility to recover the entire properties by a zoom down to that scale, and that of course is a constant line with the cooperation with Osiris that we can do, who have also a capability of getting down a few tenths of centimeter. So that's where we landed. You probably all know that. We targeted finally a place, the arrow. We finally get there, typically 100 meters from there. And remembering that that's been done at 500 million kilometers is not bad, right? So we are very happy with that. And the image in the square here is one of the 7 images taken by Rowley. This one is for 40 meters altitude, but you have that down to 7 meters actually. And that will be presented, I think, I'm not sure whether it will be presented this afternoon. I guess so. Now, the science of the rebound itself, of course, that was unexpected, and hopefully we had a few instruments that could operate or did operate during the rebounds. Part of them were supposed to operate on the ground. They operate in space. And these, coupled with the engineering data we have, give us a lot of things on the way we landed and the way we rebounded. And both MUPUS and ROMAP give us information rather rapidly, within minutes timescales, on the fact that we had not landed actually. We landed and then rebounded. And that's by the sensitivity of both MUPUS and ROMAP. If you're interested, I can tell you afterwards how they did that. So we could follow that. And the solar panels also were illuminated in a sort of sporadic ways. and also the panoramic camera Shiva P that the PI off also took images. As you know, we had planned to make a panorama just after landing to know where we were. So we did that, but unfortunately, or fortunately, I don't know, we were not on the ground. And so this here's a summary of the way the images are taken, the Shiva images, and that's what they are named Shiva actually at the god, because we have 7 heads and or 7 arms and 1 head. We have 7 cameras all around, and they are very tiny micro cameras, and the very first images that was taken a few minutes after we landed, that was downloaded immediately, and was a surprise is that image. That image on the top here that was never shown before was sort of a shock, because obviously we were not still, we were moving, right? So that image demonstrated, together with MUPUS and ROMAP measurement, that we were not on the Comet. And at that time, which was only a few minutes or an hour, let's say, after we landed, it was terrible because we didn't know at that time whether or not the ejection velocity was higher or lower than the escape velocity. So we didn't know whether we would rebound to the surface or not. So that was sort of critical at that time. It took some time to realize that finally we had a velocity smaller than the escape velocity. So the rebounds, thanks to that, have a lot of physics in that we are working on now. First of all, the question is, okay, the dumping, because again, the ejection velocity was smaller than the escape, how would the dumping occur? We had 3 systems to get on the surface. 2 failed, as you know. That one worked. The other one was the landing gear itself that was made really to dump the system. The question is still, okay, what the fraction of dumping made by our system with respect to the soil itself? There is still some debate analysis going on here, so we have some ideas already, but we know now rather accurately, thanks to the Osiris images plus all the reconstruction we made, that the escape velocity was typically a third of the incoming velocity, which was a kilometer a meter a second. So it was something like 30 centimeters a second when we rebound. We went only to a few hundred meters, but we stayed 2 hours in space, right? It was long. So that's why it was complex afterward to retrieve all the trajectory that we are doing now. And the question is, of course, why did we rebound this way? Where is the energy lost, and where the dumping there? And thanks to that, plus many other instruments that were operating afterwards, we tried to reconstruct the physical property of the surface here. And that's what I say here. We have all the dynamical parameters now. We know exactly the rotation afterwards. And we have a lot of system working. We have a wheel that was stopped but still running for 40 minutes afterwards. So when you take all that together, we have a way to understand what happened physically there and to reconstruct essentially the surface as it is now. So we know that there is a mixture of ice and dust. Typically, the dust is a few centimeters over ice. That's why, as seen from space, we knew that only dust is observable. Ice was not observed. Only now, Virtis has a few spots, but very little spots. Essentially, where you have this organic matter all around. But actually, in most of the places, this covering organic dust is very shallow, a few centimeters, and so we touch the ice itself. And the question is, okay, what is the status of this ice? And it's important just for the cometary physics itself, and that's what has been alluded by Claudia a while ago. We consider that there had been some what I call the thermally sintering process, maybe only on the very top surface, not on the bulk itself, on the very top surface, maybe tenths or centimeters or meters, which might either be like a trampoline, in other words, it helps constructing and then exports, but we don't know whether it is our system who make the rebounds or the ice itself, and this we will know rapidly, we hope. So there will be, for the building process of this crust, a paper rather soon there. And then, of course, we landed and stopped at rest. And so, meanwhile, during hours, we had 3 instruments operating, 2 instruments essentially, Concert, ROMAP, and also MUPUS. And Concert make his entire tomography of one entire plane, and that worked very well, properly. And so with that, we'll have both the internal and surface structures well understood, and that also will come very soon. And then, of course, we had all the other instruments operating. First, the panorama of Shiva, MUPUS sensing, the Sesame instruments, and then finally SD2, Cossack, and Ptolemy. So these are acronyms, and for those of you who are interested in, of course, knowing what they mean and what they did, I'm open to answer all that. And essentially, organics are, of course, the key of part of that. Following what Catherine just said, we have a huge variety of things which have been observed in the mass spectra again, obtained essentially after the first rebound. A lot of material was put in the oven themselves that both Ptolemy and Kozak would have did analyze afterwards. The analysis, of course, is still under processing now. It's ongoing. We still do not have a merged view of all that, but merging all what we have with essentially with the spectra of Kozak and Ptolemy, in comparison with what Rosina has seen kilometers away from the nucleus, we'll have an idea whether or not the same material is observed there and in situ, and if there are any differences, and to which extent we can extrapolate things. So what has been already said, of course, that CO and CO2 are the dominant species with H2O, but of course, importantly, we have a lot of organic molecules up to masses higher than 100. But again, as Catherine just emphasized, it's not trivial to ensure that the composition is a real one. So we are still working on that. Okay, so now a few words on the post-hibernation perspective. What is the status now? First of all, where are we? When we landed, this is the very first image that we got, and again, after this nightmare night, we were very happy to see that we have gone to rest. This is the very first image we got, and that's the second one with our sunlit hemisphere or part of the nucleus, and so we put these together, and this has been the very first image that we proposed November 13, as you might remember. And then when you continue here, you can see all the other images that we got, and these showed essentially that we have a foot just up, and in the background we don't know what it is. When we stress a little bit, we have that, so that is some sort of small cliff or boulder, whatever you call it, behind. And when you stress even more the dynamics, you've got to realize that the cameras are so good, if I may say so, that even if you have only 2 or 3 DNs, the noise is less when at the end. When you stretch that, you have a lot of information there. And this is absolutely gorgeous, because then this is exactly what is typically meter away on one side, and I will go back to that in a second to say, well, that's probably all around. And that's fundamental, as you will see. So what do you see here? These are the reflections of the fit from the system itself. But importantly, this is what I call the perihelion cliff, and because you might see that, just for you to know that if I call that the perihelion cliff, it's because if we were to land where we touched down, we knew that the illumination, and that's why we chose that, was sufficient to have the long-term science operating right now. That would be fantastic. But after a given time, which is typically end of February, March, we'd be too close to the sun to be able to maintain the temperature lower than the extreme. As you know, in space, you need to be lower than the minimum temperature and lower than the high temperature, and that would be reached by March typically. Thanks to the shadows in which we are now, if we have the survival, we can go up to perihelion, I hope. And so that's why I call that the perihelion cliff. It's very important. So when you just continue, the other camera here, it's essentially dark. I mean, if you do not stretch, you don't see anything. It's really 1 or 2 D and no more than that. So that is exactly what we have, we think, below the lander now. It's essentially full shadow with some light there, which is essentially reflection. And here we see the third foot, actually, of the lander. And so actually we landed, but something like that, ups and down. It was not obvious to reconstruct where we are. So we did that, as you might have seen, just to emphasize the fact that it's not, it's biased because the sun is not really as shown here, but it's just to show that essentially we are not the 3 legs on the horizontal plane. It's really something like that here. And this is something, some sort of an artist view made by the CNES Flight Dynamics, just to show the lander here. And what they have done is essentially to take our images and to see, okay, how we might be there. And this is essentially the place where you see the cliff here, right? And so that's essentially what we see. And of course, the DTM around is not made yet, and we hope that Osiris very soon will demonstrate where we are, find us, and then we'll make an accurate DTM. But the important thing is that because of that, the sun, as you can see, comes only in a rather limited angle, and so that's why the daylight is only 433 minutes for the moment, instead of half the local day, which is, as has been said, 12 hours and a half, so and 40 minutes. So we have a little less than the 6 hours that should be the normal day and night. And that's part of the reason why, for the moment, we have been forced to shut down everything here. Hopefully, in a while, we have the sun over the horizon, because we are very low in the solar elevation is very low now. Probably by, depends where we are, of course, we don't know exactly, but probably if we are in the 1,000 latitude of this comet, by February, March, we should be in that configuration then, and immediately, I would say, the energy will be sufficient to go back to operation. The only question, of course, is survival, and we think that the thermal survival by that sun is sufficient really to maintain all the systems which are off for the moment above the qualification values. Good. So what's around, it's clear. We have this on one side, and we have a lot of fractures. We have linear fractures, and this is fundamental in a sense, because as seen from other rays there, you see some blocks on a meter or hundred of meter scale, and when you go to even the Rayleigh images below the lander, you have exactly the same. In other words, we have like a fractal sort of things with fractures, which obviously are made in ices blocks. So these blocks are really blocks of ices, which are on this view here to the right, you have these, and they're exactly the same linear fractures here. So very close by, which is typically tens of centimeters, we have this material that we consider the pristine material, the graal they are looking for. And on the same block here, you have a distinct pattern here with a lot of this carbonated, probably dust that we see somewhere else, like here, for example. And so you have a huge variety of material very close by, and that's why I just emphasize here. That's very close by, and when I say close by, it's typically tens of centimeters around the lander. In a much better way that probably what was the, or what is the situation in the touchdown place, really. We have a variety of places, and that's due to the fact that we're in a hole, in the shadow of something, so essentially you have the blocks of this pristine material still there. So because of that, we have a large diversity of materials ahead of us, much larger than we hoped, actually. Probably these are the pristine building blocks with a lot of ice, loaded with the organics. We're in the process now of measuring precisely the albedo of all these things. But typically, even the ice is something like maybe 10, 12% in albedo, no more than that. So it's really loaded with these organic. This is the material that we were desperately looking for. They are there. Probably by the rotation with it, plus the capability we have to downlift the system, will be in a better position to really have the drill get into the samples and filling the ovens for Cossack and Ptolemy to operate it. And because the shadow is essentially, we are very lucky because we can probably operate longer, we have a long learn-term science. And so all what is in here that I'm not asking you to just even read is just to tell you that what we are planning now as the post-hibernation science to be completed here. So finally, and this is really the only message, it was very acrobatic. It was not obvious that we will make it. We did make it. We are in a place that was almost impossible to reach at once. Of course, you can't land close to a cliff. We are there now. There is some issues, of course, and frustration with the fact that we have to wait another some weeks or months maybe to complete the operations. But if we are lucky enough and if we are robust enough, and I think we are both, we'll go even beyond the expectation. Thank you.
I think what I want to highlight here is that as soon as the lander separated from the Rosetta orbiter was when we started the real science of the mission. So the science began then, and we continue with the science. This is what's indicated here. This is basically the orbit of the comet around the sun, indicating the 2014 aspects. But what I really want to draw your attention to are the perihelion region, and the year ahead that we have from now on, where we go through perihelion in summer next year, then go away from perihelion. We are looking at the moment at also extending the mission somewhat as best we can, given the fuel on board, and that's something we're looking into now within the team, and that will hopefully take us into 2016 even further. So that's basically the future. The key message here is that the science has only begun now. Everything else was really to enable the successful delivery and spectacular delivery of the lander, but the science began there. That's the focus of the mission now. I want to give a couple of tasters here of what we have in store, if I can find the arrow. This is a flyby. What you see on the right-hand side is the field of view of the instrument deck. You can see the wide-angle camera field of view and the nav cam. This is the closest we'll ever get to the comet. We're going to do a flyby of around 10 kilometers from the center of the comet, so we'll be about 6 kilometers above the surface. This will occur in kind of mid-February. This point is at the end of the bound orbit period. Beyond that point, we will no longer be able to be in bound orbits driven by the activity of the comet. It will just basically be blowing us away too much. So we go into these long legs far away from the comet and then do these close flybys. This one's one of the most spectacular, I would say, because we get within, as I say, 8 kilometers of the center, within the acceleration region of the coma, and also get the highest resolution images of the surface to really get an idea of the porosity and some fantastic albedo measurements therein. And a little bit further on, this is basically some of the strange orbits that we have even later on. This is around July perihelion time period, where we're targeting a flyby through a jet. So this is just before that. These large big box orbits that we're flying, around tens of kilometers, so 50 kilometers and above, and then just around perihelion, we're now, in fact, yesterday we were having a meeting where we're planning what the best spot is. We're monitoring continually where we think we will predict an active region that will allow us to plan in the long term to fly through it, which is a challenge in itself to be able to see whether we're in an active region or a jet. I use it in the loosest of terms. And I know Claudia's always saying, and other people are saying, how do you know you're in a jet? So all of this we'll find out later in the year. But this is what we have in front of us, and also in this time period, as Jean-Pierre has alluded to, we have the land of long-term science as well to look forward to once we find it and get a real fix on when that will occur. So hopefully the messages you've got that we're 1,000% science now. We've made a good choice with the Comet. We've had an exciting landing more than once, and it's actually in a better spot than we could have wished in terms of science. And so I have to reuse the word that Catherine was alluding to, this treasure chest, and it's all there for us to do. And it's really tough. I think it's true to say that most of the teams are significantly overwhelmed with the amount of data that we've got, and we're just trying to prize out the truth before we start telling you exactly what we're finding. So thank you for your attention, unless anyone else on the board here has any comments to make.
Okay, we'll open the floor to questions. Thank you, speakers. Do we have any questions?
Alex Whitsey with Nature for Jean-Pierre. Can you talk a little bit more about the specifics of the angle that you need to get the energy sufficient to wake up again, and maybe some technical details on what that flux might be on the panels?
Okay, well, to be able to wake up is two things. It's thermal and electricity. For the electricity, we need to have the solar panels with a few watts. For the moment, we have typically 5 watts there, which is sufficient to reboot the system. If we want to do something there, we need to have another 5 or 7 watts. So the question is how to get there. Either nothing changed and we just wait for the sun to be higher in intensity, and this will come later, like April, May, probably. But if now, depending on the way we are located here, the sun will go over the horizon, the local horizon of our lander, it may go earlier than that. So the question of how much power we'll get is really a function of where we are now and to try to reconstruct the DTM as it is now. So that's why we desperately try to have Osiris located us now. We have done all what we could with the data we have now, essentially with the concert things plus many others. We have reconstructed the trajectory, so we know, I think, the sort of area in which we should be, but then we need to have a precise understanding, essentially to reconstruct the DTM, the local terrain model, close to us to know where we are. So the pessimistically, it will be after Eastern, positively, and it will be much prior to that. It really depends how the sun will go over the horizon, the local horizon. So that's for the electricity, which is, again, it's the total energy we need is rather limited, right? It's less than 20, it's something like 15 watts total, which is really less than what you have in your fridge. So it's really limited. But still, we are the 3AU, so that's why we need to wait. Now the second question is, okay, do we have time, or do we have the survival capability to wait until February or so? And this has to do with the temperature inside. As you know, we have been qualified for a temperature which is typically minus 65. With a margin of 10 degrees, it means that up to probably minus 75 or 80, we are in a good shape. It's difficult to assess what the average temperature inside. The fact that we have 4.5 hours on the solar panels globally, although it's not charged during that for other reasons, it's probably sufficient. The information we got just after the last moment is that we are very close to the hibernation period, during which we had something very close to that. So we consider that the survival is warranted. But again, this we will know only when we turn on the system. And so we'll try, as soon as we know where we are, we'll do try, and that probably might be as early as January next year.
Hi, Eric Han with Science. So if knowing where you are is so crucial, maybe Matt or Jean-Pierre, you can tell us about the efforts to find the lander, what you've done so far and what you have in store, what the chances are of finding it.
It's a bit like waiting for Christmas presents. That's basically the situation. Maybe Holger can add to what I'm going to say, but I think the images have been taken. We're just waiting for them to come down. So maybe Holger can comment on this from what's being done from the NAC camera. So I'm pointing at Holger Sirks, the PI of the OSIRIS camera on board Rosetta. So would it be possible for Holger to get the microphone?
Okay, I'm Holger Sirks, the PI of OSIRIS. So we ran already 2 search campaigns, so the first on November 24th and the second on December 6th. At that point in time, the lander was in shadow, and we were stretching the images and found one candidate, but it was not significant enough to really to say yes, it is it. So we had a meeting at ESOC, so at the end of the Science Working Team meeting, and defined 3 more search campaigns for December 12, 13, and 14, which is in the past. And so with, let's say, from the best of our knowledge today, with showing the lander in sunlight, so just properly faced, and at a closer distance, so 20 kilometers to the center, 18 to the surface. So we should find the lander in these images, but it's 500 million kilometers to get the data down, and it's first in, first out, so we'll have to wait the data getting down. So we are still not in the situation that we have the data, and then the real search will start. So yeah, so we are waiting every day, so we're checking the data stream down, so they are coming down as the data was taken, so in the stream of information from Rosetta. So I can't tell you exactly when, but it's these hours, these days, so we are eagerly waiting to get the data at hand and analyze it.
That we get the data down, and then it's down to the OSIRIS team to try not to find too many lander-looking objects on the Comet, just find one.
Hi, this is Dan Vergano with National Geographic. I just want to make sure I can understand the rebound, what happened there. Was the lander tumbling, or was it just that it went up and inverted and came down? And I think somebody said it landed upside down, but then some of the images, it looked more like it was on its side. How do we properly describe that?
Okay. 2 things. First of all, as you might know, we have a wheel inside that was maintained, operating during the descent to maintain the z-axis vertical, if I can say so. It's been stopped upon touchdown, but it remained operating for another 40 minutes or so, 43 minutes. So after the first rebound, essentially the z-axis probably was maintained like that. So all the first trajectory was maintained like that. But the geometry of the impact was such that we acquire a momentum, and so we were rotating, and this we can see rather rapidly actually. So we were rotating rather fast, but maintaining this axis up to the next touchdown, in which it's more complex to know. Actually, we have some images showing that we are still in a sort of similar position with the z-axis there, but probably after a while, 1 foot went the first, and then of course we stopped here. So very likely at the very end, we really jumped like that and in a very bizarre position, and just one of the feet act as an anchor essentially. So we are anchored by 1 foot essentially in the hole here, and that's why we are sort of fixed now. And this is why when we started to implement a movement on our system, actuated movement like the drill itself or the deployment of MUPUS, essentially nothing really moved, a little bit but no more than that. So it's not that we are just oscillating now, we are sort of solidly anchored by our own system. But we are not now capable of reconstructing the last rebound. We say that we did that 3 times, it may be even more than that at the very end really. We were really close to the surface, and at the end it was really small lobes, like a few meters, no more than that. So we know for the first one, not the others.
Other questions?
For Katrin, are you seeing any evidence in your data that the lobes are different, that you're getting a different signature from each lobe? You seeing that in any of the chemistry?
We do see heterogeneity on the nucleus. So we have spots where we have much more sulfur. But if it's related to the 2 lobes, or if it's even on a smaller scale inhomogeneous, we don't know yet. But it's certain that the comet is not homogeneous.
And you don't have an opportunity to solve that now because you're so far away?
No, the problem is a little bit that we do only terminator orbits. So that's as soon as we will have the flybys, we will have more geometries, and then we can look from other sides. And I think then we will know if it's the 2 lobes which are different, or if the lobes by itself are very heterogeneous.
And Jean-Pierre, you're very confident, are you, that Philae will come back to life? You believe that you will be doing more science with the lander?
Well, you know, it's not a matter of belief, really, in science, as you know. I think we managed to make a very robust system. And although some of the system failed, we are still there. Now, the question of survival, again, which is the only really question of importance, I think is solved to me. That we'll know only when we're there. So I cannot say more than that. We do as if we get prepared for a positive get out of hibernation. Now, what else can I say? We don't know. We do not see anything's broken because all the system worked perfectly. The deployment worked. Everything worked. So really, the question is whether or not some of the electronics might suffer from the cold. But we think that most of the things outside already went through very low temperature during hibernation, and that worked very well. Our camera, for example, can run down to minus 150 degrees C, and there are no problem with that. So a lot of our systems were designed to sustain very low temperatures. We knew that we would have to operate in a very low temperature environment. The only question is really the inside, and we have isolated, so the question, it goes both ways. So we have thermal absorbers on the top surface that takes every photon there and modify that. We measured the increase in temperature every daytime during the 4 days we were there. It was very positive. So yes, again, when putting all that together, I think within the team, there is no doubt that we will wake up. And the question is, okay, in which shape? And my suspicion is that we will be in a good shape. Well, in the brain, more than the heart. You know, we know that the heart was in the old time. In the Middle Age, we thought life come from the heart. We know it's come from the brain.
Paul Doherty from the Exploratorium, and for Catherine. So Philae bounced on the surface, and or maybe for Jean-Pierre, Philae bounced on the surface, kicking up dust. Did the instruments detect what the dust was made of, and then get a different answer when it was 100 meters above the surface?
Okay, I'm not Catherine, but still. Okay, most of the results we have now are from Kozak and Ptolemy are the analysis of the material which has been collected after the rebouncing. And actually, we can measure the difference in the material collected after all the bouncings, and because we did several measurements afterwards, and the higher was after the first one. So yes, we consider that most of the results that you will see soon come from the analysis of what was on the top surface, blocked in the ovens and then analyzed. And so the answer to your question, whether or not that's different from what ROSINA has found, we will know soon when we have completed the NLI there. Obviously, there are things which are identical, like the CO2, for example. Even the ratio CO2 might be different, and so we'll see whether or not the CO2 comes from CO or conversely. So yes, we'll have the answer to that, I hope soon.
Rick Lovett, freelance. I'm interested in the deuterium. Two questions here. If I understand correctly, you've now ruled out both Kuiper Belt comets and Oort cloud comets as this major source of Earth's water. And the second one is, how do you know that this one is one that formed inside of Neptune and was kicked out during the Nice process rather than formed in situ out in the Kuiper Belt?
Our comet was formed outside of Neptune. It's not one of, it's not the Oort one. The Oort clouds were formed inside, and ours is, I think, a real Kuiper Belt comet. And from all what we see, it speaks of very cold temperature, which means that it was formed very far out. Yes, we now have ruled out both reservoirs of comets. But you know, I'm quite a long time in this business. I started out with Giotto, and it's always changing. Before Giotto, we had only Oort cloud comets. Then we invented the second reservoir, the Kuiper Belt, and then they started to mix, and today I think we have a big mixture of everything in everything. So things tend to become more complicated. So comets can migrate from one reservoir to the other, and so you even Hartley 2, which is terrestrial, may have just migrated into the Kuiper Belt reservoir from somewhere else.
We have a new classification of asteroids called main belt comets that have coma and tail. So we are discovering more and more about our solar system as the decades roll on, and we have work to do to put all these pieces of data together to understand, you know, how it all fits together in terms of the origins and what reservoir fed another.
I have a question from Leo Enright from Irish TV via the web chat. And his question is for Jean-Pierre. Can you please address the large-scale topography? The 5 a.m. picture shows massive landslides. How do you get that on a small body?
So if the answer is yes or no to the question, can you do whatever, the answer is no. The people are processing data now. Concert data are really complex, I must say. And the tomography is still ongoing. So I cannot for the moment tell you whether or not they have found any sort of differentiation or modification of the density as a function of where you are in the body and whether the two lobes are different or not. This is achievable. That will be achieved. It's not done yet.
Okay, I have another question from the chat. This question is from Irene Klotz from Discovery Channel. She says she'd like to know if Philae's drill samples were able to be analyzed and any results radioed back to Earth before the lander shut down.
So if I got well the question, which I'm not sure, the question is whether or not the SD2 system taken its sample to the oven, and that's whether or not it's been analyzed. We don't know the answer to the question precisely, definitely. We think that, I mean, it's obvious that the SD2, the system worked perfectly. We see it operating up to the surface and then down there taking the samples and designed to put this sample in the oven. The measurements made by the Cossack afterwards do not demonstrate any increase in any material afterwards. So it may mean different things. Either SD2 didn't go to the surface, or it went to the surface and could not distribute these samples to the oven, or just something else. And this we just do not know. One of the possibilities, for example, is that if they touch a very hard surface in a given pattern, they couldn't enter because at the time they just sort of drill. It would make essentially the lift of the rover, of the lander itself. So no, for the moment we don't know. The only thing we can say that the GC that operated after the deposition or steady deposition of the samples in the oven did not detect any amount of material there. But again, that's still, the process of the NLI is still ongoing.
I have another question from Tracy Watson at USA Today, and this question is for Matt Taylor. Do you know more about why the harpoons and gas thruster failed? If the harpoons had worked, would the lander have anchored or bounced back into space?
There is an ongoing plan to have a review of exactly what went on. So with the Lander Consortium and also ESA, this is planned to happen. It hasn't happened yet. And as for what would have happened and what happened, one can only speculate. I think Jean-Pierre was alluding to the fact that the surface appears to be very, very hard. So one could also say we didn't do too badly that the harpoons didn't work. Otherwise, we might have had two orbiters. So, yeah. But this is you know, in the near future there will be a review to see exactly what happened.
Thank you.
Do we have more questions from here in the room? Do we have more from the chat?
I do have a few more. Just a follow-up clarity question for Jean-Pierre. Earlier you were saying, you were talking about survival and they had a hard time hearing you. Can you just repeat a little bit what you said earlier, please?
Sure. Again, we know that just by approaching the sun, the comet will go to a much better position in a while. And so we are sure that in terms of the energy available, it's just a matter of waiting. And typically by February, March, April, it will be close enough, if anything else change, just to get enough energy to operate normally. So the only question is, do we have the capability to wait until that comes? And the main issue there is thermal. Do we have the capability to sustain the temperatures, which are the present temperatures, although we don't know exactly what they are actually. And what I said is that given what we measured during the 4 days we were there, the evolution of the temperature there, the extrapolation of that gives us high confidence that we are in an environment that should allow us to survive until the energy on the solar panels are back to what we need.
Thank you. And one more question from Leo Enright at Irish TV. When you say ice, do you mean ice 1, ice 2, or ice 3? And where's the experience of dealing with such a, I think he means, what is the experience of dealing with such a cryogenic landscape?
The question is to
There's
me,
nine phases, so why limit yourself to just 3?
Yes, and actually we might be in the number 10 because no one knows really what the, you know, we always extrapolate with respect to what we simulate in our labs. And obviously what we have there is very different. We have a very porous system. The density, the global density we know is less than 0.5, it's typically 0.48. And essentially made of ice. So you have a lot of way to consider, okay, what is the sort of snow that we have in that sort of things. But then you put that to very low temperatures, plus the cycling of the time. And what obviously happened is that, and it's never been simulated to very high accuracy really, that the top surface at least goes to a status, a phase, which is not really necessarily one of the one we had in mind. It's not amorphous probably in the sense that, okay, you might have crystal there, but the way it's transformed thermally, that's what we proposed this question of the thermally sintered things. It's very rigid. Again, prior to be there, we thought that the major risk was not really to rebound, but to sink in the system, to break the crust and just to go through. And that would have been lethal for us. We understood now that the crust is rigid enough really to avoid that and to preclude the sinking and even to probably not only enable rebouncing but maybe favor the rebouncing. So now that we know that, of course, a lot of people will work on this simulation there, both by modeling and by real simulation, just to see, okay, how can we make that? And we go back to what we call the COSI instruments, or the COSI experiment that were done 30 years ago, even more than that, in Germany.
KOSI.
Yeah, the COSI. That was a huge lab things made in Heidelberg in Germany at the time of the Giotto encounter, just to understand what the comets might look like. And now that we go back to that, we observe that in some cases, top surface of the ice also makes such a crust that we should maybe have considered more than what we did actually. But so we are working on that now. But the result is that obviously the top surface is not only one of the 3, but maybe one of the 10 sort of ices.
So that's why we brought up the physics of sintering, which is how this, it's a strange water-ice mixture in a low-gravity environment that can be potentially very strong. So we look now back at some of these old experiments.
But of course, the outgassing, the activity of the comet is part of the processes. I mean, it's just that not only that you put ice and then you wait. You put ice and then thermal after thermal cycles, you modify the top surface. And this is really what we are on now. And this was not expected, of course, very difficult to expect. And so, again, it's not just that you put ice and you just thermal it in. You put ice with a lot of things ahead, inside, and then you sublimate all that, and you are left with what is left. And that's the sort of ice we have.
Thank you. I have one more question, again for Matt Taylor from Tracy Watson at USA Today. And the question is, do you think that MUPUS pen and SD2 will be able to gather data in the spring, assuming the lander survives?
My assumption is that once we get the lander back online again, we'll be able to do more science, and we have a better feel for making the science even better. I mean, Jean-Pierre might want to add to that, but we'll have we've done our first science sequence, and we will be initiating the long-term science, which was planned.
Yeah, we can essentially redo all what we had planned to do during what we call the long-term science. So everything, SD2 in particular, will be reoperated in a better way probably because we are closer to the surface now, and we have the possibility to go really in the subsurface, we think. For MUPUS, it's a little different because MUPUS is a set of different instruments, but one of them, which is the deployment mechanism, has been deployed once. We cannot now redeploy it. So MUPUS, as it is now, the deployment, what we call the pen, cannot be redone. That's unfortunate, but that's the case. APX, for example, has been deployed once. It can be retracted and redeployed. So everything can be redone except the deployment of the MUPUS pen.
Thank you.
Okay, do we have a last question? Okay, this is it. Thank you very much, speakers, and thanks everyone else for being here. Our next press conference is at 10:30. It's the Arctic Report Card 2014.